Hello, this video is on the history, properties, and applications of flash memory, narrated by Veer Pandya. Flash memory is widely used in a variety of applications, including memory cards, flash drives, solid-state drives, and random access memory. Some popular consumer technologies that take advantage of the benefits of flash memory include computers, cell phones, digital cameras, video games, and medical devices. Flash memory was first invented by Fujio Masuoka of Toshiba back in 1980. It was developed using a modified version of electronically erasable programmable read-only memory. Intel Corporation realized the incredible potential of this technology and started working towards what would become the first consumer-grade flash chip released in 1988. This technology was labeled flash as its writing process resembled the instant flash of a camera. Flash memory has two main types of gate structures, NOR and NAND. NOR architecture was the first to be utilized. NOR-type flash has relatively long read and write times but allows for immediate access to any individual bit of memory. This proves to be very useful for applications that do not need to be continuously updated, such as BIOS chips in computer motherboards or firmware chips in devices such as wireless routers. NAND-type flash memory has much faster read and write times and also takes up a smaller area, allowing for greater data storage than in NOR-type flash. The downside is that information cannot be accessed bit by bit, but rather in data structures known as blocks. This means that NAND-structured flash memory cannot be used as a primary device storage in devices such as computer processors that require individual memory addresses, but prove to be rather useful in secondary mass storage such as SD cards and USB flash drives. There are two types of flash memory: memory that require constant power, known as volatile memory, and memory that does not require constant power, known as non-volatile memory. As its name suggests, volatile memory is only stored temporarily, as long as power is supplied to the device. The two main types of volatile memory are dynamic random access memory, or DRAM, and static random access memory, or SRAM. DRAM is cheaper to produce and also requires less area, but necessitates continuous refresh cycles. This is useful for devices such as graphics processors where a very large amount of memory is required. SRAM is faster and consumes less energy than DRAM. This is more useful in devices where speed is much more important than capacity, such as in cache memory in processors. Non-volatile memory does not require constant power in order for the information to be stored. This proves to be typically slower than volatile memory. Due to the nature of the gate structure, non-volatile memory devices have a shorter lifetime of read-write cycles before the hardware fails. Given these disadvantages, non-volatile memory still proves to be incredibly useful for storing data long-term in media such as memory cards or solid-state drives. The cell structure of flash memory devices resemble a standard NPN MOSFET layout, with the exception that there are two gates for every transistor made from highly doped polysilicon. Each transistor has a float gate, which stores the bit of information, and a control gate, which allows charge to be applied or removed from the float gate. The float gate is electronically isolated from all sides with an oxide layer, meaning that an applied electric field is the only way to store or remove charge. Electrons stored on this gate represent a logical 0, and vice versa, a lack of electrons represent a logical 1. In order to store information, two main techniques are used. In NOR-type architecture devices, hot carrier injection is used to write information to the device, and Fowler-Nordheim tunneling is used to read information from the device. NAND-type devices use Fowler-Nordheim tunneling to both read and write information. Hot carrier injection is done by applying a large voltage to both the drain and control gate of the transistor. This results in the control gate repelling positive charge away in the p-type substrate, creating an inversion layer. This allows electrons to gather on the float gate, trapping them there until an electric field is applied to remove them. Fowler-Nordheim tunneling consists of applying a large electric field in order to instill a charge to the float gate. To remove that charge, a negative electric field can then be applied. In NOR-type devices, each cell structure has one end connected to ground and another end connected to the bit line. A logical 1 is the result of current flowing through the gate such that the bit line is pulled down. This architecture provides for individual cell access and direct code execution from the stored information on the device. In NAND architecture, multiple cells are connected in series, resulting in a structure known as a block. The advantage of this is that more bits can be stored in a smaller area due to the fewer ground wire and bit line connections. However, this results in the data only being able to be accessed block by block rather than bit by bit, which is not suitable for the low read latency requirements of devices such as computer processors. In this gate structure array, the bit line is pulled low only if all word line inputs are high. In conclusion, there are many advantages to flash memory technology. Overall, flash memory has very fast read and write times than other competing technologies such as mechanical hard drives and optical disks. Due to the solid-state nature of the components, flash devices are extremely durable and not as sensitive to physical damage or magnetic fields. Flash memory is currently used in a very wide range of devices, and modern devices are far smaller than any of the other storage solutions. There are very few downsides to using flash memory as of today. One of the most notable disadvantages is that flash memory is more expensive per megabyte of storage compared to traditional media like hard drives. Flash memory also only has a certain number of read-write cycles before the physical hardware fails. To prevent rapid degeneration of the transistors, modern SSDs have write protection mechanisms set in place. However, not all flash devices are able to use this feature. Some notable modern developments are the invention of vertical NAND gate structures and 12 nanometer size architecture. Vertical NAND is created by stacking the gates physically vertical. This allows for higher bit densities per unit area while not needing to decrease the individual cell size. This technology offers nearly twice the speed of traditional NAND layouts and up to 50% less power consumption. The future of flash memory looks to eliminate one of the biggest downsides, which is the cost of the chip. Companies are continuously finding ways to decrease cost while increasing storage capacity. However, this comes with a limitation in cell size reduction, as eventually there will be a point where cells are not physically able to be scaled down further.